In this section, we will review how to build a logistic regression model in SAS. We'll take a look at proc logistic, which is the procedure used to generate a logistic model. We'll take a look at the options within a proc logistic, and we'll take a look at the output that is generated from a logistic regression. So there's a code here, proc logistic code, and I'm just going to review it. So you start off by using proc logistic. Data equals to specify the data sets, and then there are some options here. There is descending, outtest, and then there is a model statement. Now the model statement is the syntax of the proc logistic is similar to proc reg in that sense. You need a proc statement followed by a model statement. The model statement typically follows y equals to x1, x2, x3, where y is your dependent variable, x1, x2, x3, etc. are your independent variables. So we have the same setup here. Proc logistic data equals to dataset, model, loan eligibility, which is my dependent variable, is a function of income, prior credit score, and employment status. So here we have three different independent variables. So that is the minimum requirement for a logistic procedure. The others are options, which I'm just going to cover now. The first option is descending. Now descending is used if you want to model the probability of event equals to 1 rather than 0. In fact, how this works is that remember, in a binary logic model there are two values of the dependent variable, 0, 1, 1, 2, 3, 4, whatever it is, but essentially two values. So let's assume that you have a variable coded as 0 and 1. By default, SAS will model the probability of event equals to 0. If you want to model the probability of event equals to 1 instead, then you have to use the descending option. Now, in other words, SAS will model the probability of default for the lower value event. So of course, if your variable was coded as 1 and 2 instead of 0, 1, then SAS by default will model probability of event coded as 1. If you only want the probability of model coded as 2, then you should use the descending option. So it's an optional statement. The outtest statement essentially outputs the parameter estimates to a dataset specified. In this example, model X will be the dataset that will contain the parameters from the logistic model. So then you have the first line, proc logistic data equals to descending outtest. Then we have the model statement. Following the model statement, there is another optional statement which is lack fit. It generates a goodness of fit table to assess the robustness of model fit. It's an optional table. Even if you don't have this, you will still get a lot of logistic output, but one particular output you are not going to generate, and I'm going to show you which of these outputs it is. So what we should do now is essentially go to SAS and run a logistic model on the dataset that we've been dealing with, which is the credit screening dataset. So before I run the model, let's just make sure that we understand the data. So I have a dataset here called prep, which is my dataset. It has 4 variables. Good, bad is my dependent variable. I have 3 categorical variables: credit history, employment tenure, and income. And all of these, my independent variables, are categorical. Now, one thing about good, bad, the way it's coded is that 1 is the probability of not defaulting on the loan, or 1 is not probability, I'm sorry. The way the good bad variable is coded is 1 is if this person has not defaulted on the loan, 0 if the person has defaulted on the loan. This is historical data. So 1, 0 essentially tells you 0 is if this that particular person, applicant, defaulted on his loan. 1 is if they did not default on the loan. So this is my data set. What happens when I run a proc logistic? Let's take a look at the output. You can see that a fair amount of output has been generated. There are multiple tables here, and we'll of course review all of these tables one by one. There is a model information table, there is a response profile table, there is convergence status, there is model fit statistics, there are the parameter estimates, which is what we are familiar with from doing linear regression. There are the odds ratio estimates, and then there is a concordance table, finally followed by a Hosmer-Lemma test. This particular table is what is generated when we specify lack fit in the model statement. If you don't specify it, you will get everything else other than the last final Hosmer-Lemma table. So now let's essentially review what each of these tables tells us and how to interpret results from each table. Let's start with the first set of tables, which is the model information tables. Now, this is just descriptive information about the data set, the variables, and the response variables. For example, for this particular logistic output, it tells us we've used a data set called prep, which is in the work library. It has the response variable that we are modeling is the good bad. There are two levels in the response variable. Remember, we have only 1 0, and of course a logistic can be run for multiple response levels. So I could run a multinomial logic for multiple levels, but so then you would have more than 2 levels here. But for this particular example, we are running a binary logic, which is what the model option tells us. It's a binary logic. The optimization technique is something called Fisher scoring. It's just a technique that we are using to come up with the final logistic model parameters. Then it tells us that there are 1000 observations that were read in the input file, but only 999 were used in the model because perhaps one of the variables had a missing value. Right? So the number of variables that went into the model are fine. The number of observations that went into the model are finally 999. Also we have a response profile which tells us how many goods and bads we had. So we had one, the number of observations with a value of 1 was 699. The number of observations with a value of 0 were 300. SAS is also telling us that because we used the descending option, it modeled the probability of event equals to 1 and not of 0. Remember, event equals to 1 is the probability of not defaulting on the loan, and 0 is when someone defaulted on the loan. Now let's go to the parameter estimates, and I'll come back to the intermediate tables in a while, but let's just start with the parameter estimates because we are a little familiar with interpreting parameters in a regression equation, and the logistic is after all a regression. So you can see that there is an estimate table which is your beta estimates, there is standard error, there is a walled chi-square, and then there is a probability of greater than chi-square. Now the two main things to look at obviously are the estimates and the p-values. Now even though this p-value is probability of chi-square, in terms of interpretation you would interpret it exactly the same way as any other regression output, which is if I had a cutoff p-value of 0.05, because I want to be 95% confident, I would compare the p-value for each parameter against the cutoff, and if my p-value is lower than my significance level, I will essentially conclude that this is a statistically significant beta estimate, or there is a statistically significant relationship between the independent variable and the dependent variable. Right? So the reason that it is a chi-square is because remember the logistic regression does not work on ordinary least square. So it turns out that the distribution that you use for the beta estimates, the beta estimate by the standard error of the beta estimate follows what is called a walled chi-square distribution, and therefore you get a p-value associated with a chi-square distribution. Let's take a look at the estimate per se. So for example, the estimate on credit history is 0.4888. Now, as with any other estimate, we have to think about the sign of the estimate and the significance of the estimate. So let's take a look at the sign of the estimate. How do I interpret 0.488? It essentially, high level, it looks like there is a positive relationship between credit history and non-default. Remember, I am modeling probability of event equals to 1, so the likelihood of not defaulting. And what this is saying is that if my credit history levels go up, meaning if my credit history is better than let's say another applicant, the chances of me not defaulting are higher. Right? Now remember, and this is very important, that your y variable is really the log odds of the probability of non-default. Right? Remember, our y variable was log of p over 1 minus p, where p is the probability of not defaulting. So essentially the way to interpret this coefficient is to say that if my credit history level increases by 1, right, and remember credit history was a categorical variable and higher levels meant better credit history. If I go from a lower level to a higher level, the log odds of the probability of not defaulting on the loan go up by 0.4888. Now is that reasonable? Yes, because I would expect that as my credit history improves, then fewer people at higher levels of credit history will default on my loan. So this is a very reasonable result. Right? The thing to remember here, of course, is the fact that the y variable is the log odds of the probability of not default. It is not the probability of default, non-default. Right? It is the log odds of the probability of non-default. Now, how do we convert from a log odds to a probability? Right? Remember that my y variable is log of p over 1 minus p. So if I want to get directly p over 1 minus p instead of the log variable, then I simply take the exponent on both sides. So I say exponent of log p over 1 minus p equals to exponent of my right hand side of the equation. The exponent and the log will cancel out, and I will end up with something like this: p over 1 minus p equals to e to the power beta 0 times e to the power beta 1 times credit history times e to the power beta 2 times employee status, etc. Now notice that instead of a plus sign, we now have a multiplicative model. So if you take the exponent for if you take an exponent of an additive model, it becomes a multiplicative model. So I can actually calculate p over 1 minus p by substituting the beta 0 beta 1 values like this, and I will get essentially an equation like this: 0.624, which is the exponent of beta 0, times 1.63 times credit history times 0.68 times employment status times 0.89 times income. And what this implies is that if credit history goes up by one level, the p over 1 minus p, which is my odds ratio, right? Remember, why is p over 1 minus p now? We've gotten rid of the log. My odds ratio of the probability of not defaulting goes up by 1.63. So an increase in the credit history by one level increases the odds ratio of being sanctioned a loan by 63%. My odds ratio of being or not defaulting on a loan or being sanctioned a loan goes up by 63%. That's how I would interpret it. Right? What about the employment status? Remember, the employment status was negative. I have a negative coefficient minus 0.37. Now remember, the employment status variable in our data set actually had 0, 1 values, 0 meaning employed and 1 is unemployed. So essentially the way to interpret this is to say that going from employment status of 0 to employment status of 1 reduces odds of being granted a loan by 37%. This is 0.37, so 37%. It reduces, because of the negative value, it reduces odds of loan by 33%. 37%. I'm going to redo this slide. Now, how do we convert from a log odds to a probability value, which is not a log form? The easy way to do that is to simply take exponent on both sides. So you say that instead of having log of p over 1 minus p equals to beta 0 plus beta 1 times credit history plus beta 2 times employment status, what I'm going to do is I'm going to take log on both sides. So then I will get p over 1 minus p equals to exponent of beta 0 times exponent of beta 1 times credit history, and so on. Notice here that I've gotten from an additive model to a multiplicative model. Instead of beta 0 plus beta 1 plus beta 2, I now have e to the power beta 0 times e to the power beta 1, and that is because I have taken exponent on both sides, and you can convert. Therefore, if you take a exponent of an additive function, you will get a multiplication. Now, what does this mean? I can substitute the values of beta 0, beta 1, beta 2, and I will essentially get this exponent of minus 0.47 plus exponent of 0.48 into credit history, and so on. If I do that, this is the final equation that I'm going to get. P over 1 minus P, and P is the probability of not defaulting, equals to 0.624, which is exponent of negative 0.47, times 1.63 times credit history, times 0.68 times employment status, etc. Now, what is the right interpretation of 1.63, 0.68? This is how we would interpret it. We would say that increasing credit history by one level increases the odds ratio of being sanctioned a loan by 63%, because we have 1.63. Relative to the base, there is a 63% increase in the odds of being sanctioned a loan or not defaulting on a loan by 63%. What about the employment status? Remember, if you see a 0.68, this is less than 1. So relative to the base, there is a 32% reduction in odds of being of defaulting on a loan when you move from 0 employment status to 1 employment status. In our data set, 0 was employed, 1 was unemployed. So this makes sense. This equation is essentially saying, and the reason I've got 32% is 1 minus 0.68. The base is always 1 because you're using a multiplicative model here. So the base is 1. Right? So relative to the base, keeping everything else constant, going from an employment status of 0, which is employed, to an employment status of 1 will reduce the probability of non-default by 32%, 1 minus 0.68. If I did that for the income level, remember income is also a negative coefficient, and therefore I've got exponent of negative as 0.89. So if my income level goes up, then the probability of not defaulting according to the model reduces by 11%. Now that's not a very reasonable result, and of course this is not a significant result if you remember the table, but that's how you would interpret the 1.63, 0.68, 0.89. Remember 0.68 essentially means less than 1, which is the base, so 32% reduction. Now we had in our model categorical variables and we didn't have a continuous independent variable. So of course one of the questions that we need to address is, will it make any difference if I have a continuous independent variable? Right? And how will I interpret the change in a continuous variable? The interpretation is very similar. For a unit change in x, the log odds of the probability of the outcome changes by beta, or if you want to express it in odds ratio and not log of odds ratio, then a unit change in x will lead to a e to power beta change. Now most often we are not interested in unit changes, we are typically interested in a c unit change. So then it will simply become e to the power c beta changes in the odds ratio. Right? So instead of saying that my category, I'm looking at a change in my income from $1 to $2, you will say what happens if my income goes up by $10,000. So then it will be e raised to the power c beta. Another thing to remember is that a constant change at all levels of x may not be appropriate. Right? So what I mean by this is that, let's think of income, for example. Now, as your income goes up, the probability of not defaulting should ideally go up, but it may not go up at the same rate. Right? So the probability of not defaulting when your income is 20,000 going up to 30,000 may not be the same as the probability of not defaulting when your income is 100,000 versus 110,000. So how do we capture something like this? It may be better when you have a continuous variable to bin it and then create dummy variables, because that will allow for varying levels of change of response for different levels of change in x's. So it may be a good idea to, even if you have a continuous variable, to think about whether or not it would be better to bin the variable. Now I have still only computed p over 1 minus p, right, which is the odds ratio. Now if I wanted p, I can still do that. I simply need to substitute it into this equation. Here pi stands for p, so if I had p over 1 minus p equals to that equation, if I wanted to solve for p, this is what I would end up doing. So in our example, right, if supposing I said that I have a new customer whose employment status is employed, so employment status equals to 0, income range value is 2 and prior credit score level is 2, I can determine the likelihood of this customer being sanctioned a loan, in other words the likelihood of this person not defaulting on a loan, by substituting my beta values and my x values into this equation. So the probability that this customer is not going to default on a loan is going to be 0.79. Right? There is a 79% chance that this particular customer with these levels is not going to be defaulting on a loan and therefore will be sanctioned a loan. 79% chance. So if I wanted straight probabilities, I simply have to substitute it in this equation. So that is how you would interpret the parameter estimates and the p-values. So just re-summarizing here, we have 3 different independent variables. Only one is significant. Only the credit history is significant. Credit history has a positive relationship with the probability of non-default. Employee tenure also turns out has the right sign, because the way the tenure variable is defined is 0 is employed, 1 is unemployed, and therefore if you go from 0 to 1 you will expect that the probability of non-default will reduce. The income variable doesn't seem to have the right sign, but it is also highly insignificant, so you may not be able to rely on this result. We've also looked at how to actually capture the impacts. If I wanted log odds, if I wanted the impact in terms of log odds for the credit history variable, a unit change in credit history going from one level to the other will increase the log odds of the probability of non-default by 0.4888. We also saw that if I didn't want to get it in log odds ratio, but I wanted the impact in odds ratio, then a unit increase in credit history level will increase the likelihood of non-default by 63%. How did I get that? e raised to the power beta 1 was 1.63, and because this is a multiplicative model, my base is 1. There is a 63% increase in the odds ratio of not defaulting, based on the model, for a unit increase in credit history. If I wanted actual probabilities and not odds ratios, then I would substitute the x values in this equation. So we saw that if, for example, I was given a new customer whose employment status is employed, income is 2, prior credit score range is 2, we can calculate the probability of this customer being sanctioned a loan based on his probability of non defaulting as 79%. So this is how we would interpret the parameter estimates in a logistic regression. Now, how exactly are the p-values obtained? It turns out that the p-values, and I mentioned this a little bit earlier in some of the slides, that the beta by the standard error of beta actually follows an approximate chi-square distribution with 1 degree of freedom. In fact, the beta by standard error of beta follows a normal distribution. So you could potentially get p-values for a normal distribution as well, but beta by standard error of beta square follows an approximate chi distribution, and the p-values are generated based on the chi distribution, and the interpretation of p-values is exactly the same as any other hypothesis. The lower the p-value, the more statistically significant is the relationship between your independent variable and your dependent variable.